Hey there, how's it going? Alright, welcome. We're going to be working in section 13.3 with trigonometric identities. Now, one of the things that I'll do in this video is I'll remind you what a trigonometric identity is because we've worked with them before. And in the first couple of videos for this section, I'm going to focus on deriving a couple of new identities. In particular, I'm going to show you how you come up with the double angle identities for cosine and for sine. And you'll understand exactly what those mean here in a little bit. Alright, so you see the goal here is that we're going to derive the double angle identity for cosine. Well, let me tell you what an identity is first before we get into that. An identity, if you'll recall, is an equation that's true for all values of the variable in that equation. An equation is true for all values of its variables. Now down here where I have examples, I'm going to give you trigonometric identities in particular. Let me give you an identity that's not trigonometric that you're familiar with, just to reinforce this definition. You, for instance, ought to know that a squared minus b squared is equal to a plus b times a minus b for all values of a and b where that expression is defined. And that expression will always be defined, it turns out. And that is an important caveat here. An identity is only going to be true whenever it's defined, but it's true every time it's defined. Now, I'll get to that later on if it's more relevant. Let me give you some examples of some trigonometric identities that we have talked about. One of them is this. You know very well at this point that the tangent of any angle theta is equal to the sine of theta divided by the cosine of theta. Alright, now here's an example of where I'm saying an identity is true for all values of its variables where the function is defined. We can't let cosine of theta be equal to 0 here because, well, then you'd have an undefined tangent value, right? But as long as the cosine of theta is not equal to 0, you can always divide the sine of an angle by the cosine of an angle to figure out its tangent. Another trigonometric identity that we talked about back in chapter 11, but we haven't really put to use so much, is what's called a Pythagorean identity. Sine squared of theta plus cosine squared of theta is equal to 1. Alright, you might remember I made a bad joke, a corny joke about that. Anyway, sine squared of theta plus cosine squared of theta is equal to 1. Now, I don't care what angle measure you sub in for theta. If you sub in 45 degrees, the sine squared of 45 degrees plus the cosine squared of 45 degrees is equal to 1. If you sub in 200 degrees, the sine squared of 200 degrees plus the cosine squared of 200 degrees is equal to 1. Works for radians just like it does for degrees as well. Now, a couple of variations of that particular identity are going to be useful within this video, so I'm going to write them down. It follows easily from that identity that the sine squared of theta is always equal to 1 minus cosine squared of theta, or that cosine squared of theta is equal to 1 minus sine squared of theta. Alright, again, we're going to use this particular set of identities within this video. Alright, what we're going to be focusing on in this video are what are called double angle identities. Now, you might remember another time where we were solving equations where you had multiple angles, like you were solving for a cosine of 2 theta or the sine of 1/3 theta, that kind of thing. Well, anytime you're solving, you have an expression that's the cosine or sine or tangent of 2 theta or 2x, you have what's called a double angle. 2 theta is twice as great as theta, right? And it turns out that the cosine of 2 theta is always equal to 1 minus 2 sine squared of theta. Now, I'll give you a little bit more background to understand exactly what that means later on. But for now, what I want us to do is prove or show that this is the case. So, here's the way I'm going to go about that. I'm going to draw an angle theta on the unit circle in the first quadrant, and then what I'm going to do is I'm going to reflect that angle in the x-axis, and the goal in doing so is I want to be able to make an equation that ultimately relates an angle theta with twice its angle. And when I reflected that angle theta right there in the x-axis, what I've done is I've created a larger angle that is twice the original angle. Because you would agree, if you don't think about standard position anyway, that this angle right here is equal in measure to this angle right there, right? So this entire angle, then you would have to agree, is equal to 2 theta, right? Okay. Next, what I'm going to do is I'm going to make a triangle out of those 2 radii that I just drew by connecting them like so. And let's talk about what the dimensions of that triangle are. 2 of the 3 sides of the triangle are a radius of the unit circle, so they are 1 unit long. And then that green segment that I drew, we're going to think of it as by comparing the top half with the bottom half, or really just considering the top half and then the bottom half is what I ought to say. If you just look at the top half of that angle, well, isn't that equal to the sine of theta? Because that's just the vertical distance to where that radius intersects the unit circle for an angle theta in standard position. All right, we just reflected that point in the x-axis to make this point right here, so that means this distance is also equal to the sine of theta. And so I can say that entire third side of the triangle is equal to 2 sine theta. All right, now again, I'm trying to relate twice an angle with just the angle. And I'm going to be able to do that with that triangle that I created. Now that triangle, there's nothing special about it. It's just a triangle. It happens to be isosceles, I suppose, so that's something special. But what I'm going to do is I'm going to relate the 3 sides of this triangle, all right, this 2 sine theta and the 1 with this angle 2 theta right here. And I'm going to do that using the cosine rule. Now you might remember one of the variations of the cosine rule was this formula right here. The cosine of an angle equals the sum of the squares of the legs adjacent to that angle minus the square of the opposite side from that angle divided by twice the product of the legs adjacent to that angle. All right, you've used that formula many times. And what I want to do is I want to apply that to this triangle right here. In this case, the angle A that I'm using would be this combined pair of angles right there, 2 theta. So I'm going to say that the cosine of 2 theta equals, and then what I'm going to do is I'm going to square the 2 legs adjacent to that angle, the ones, and add them together. And I'm going to subtract the square of the opposite leg, or opposite side of the triangle, which is the 2 sine theta. Okay, so we'll have minus 2 sine theta squared over twice the product of the angles adjacent, of the sides adjacent to our angle. So 2 times 1 times 1. All right, now let's do a little bit of simplifying here. What that's going to do is give me 1 squared plus 1 squared, or 2 minus, and then if you square 2 sine theta, you're going to get 4 sine squared theta over, and then 2 times 1 is 2. And then since each of the terms in the numerator is divisible by 2, I can go ahead and make that 1 minus 2 sine squared of theta. So I just proved to you that the cosine of twice an angle is equal to 1 minus 2 times the square of the sine of that angle. Now let me give you an example of what that really tells you, just to show you that this works. Let's pick any angle that you know the sine for. Let's say we pick 60 degrees. All right? Well, if theta is 60 degrees, then 2 theta would be twice that, or 120 degrees. So what this equation would be saying then is if I took the cosine of 120 degrees, that should be equal to 1 minus 2 times the sine squared of 60 degrees. All right, so notice this angle is twice that angle. Now let's go ahead and substitute in the values that we know for these things to show that it's true. You should know that the cosine of 120 degrees is negative 1/2. All right, so that's going to be equal to 1 minus 2 times, and then you know that the sine of 60 degrees is the square root of 3 over 2. So the sine squared of that, we'd have to square, okay? Now that's going to be equal to negative 1/2, or that means that negative 1/2 is equal to 1 minus 2 times 3/4, right? You square the square root of 3 over 2, you get 3 over 4. And then that becomes 1 minus 3/2 on the right side, which is equal to negative 1/2. All right, so for the particular value of theta we chose, that equation right here was true, and it would be true for any angle that you choose. All right, now there are two more versions, it turns out, for this cosine double angle formula, but we've seen that you can find the cosine of twice an angle using the sine of the angle. Okay, now we'll go pretty quickly through these next two. They don't require pictures or anything, not quite so complicated. Next, I'm going to show that the cosine of twice an angle is equal to twice the cosine squared of that angle minus 1. Okay. Now we just established that the cosine of 2 theta is equal to 1 minus 2 sine squared theta. And what I'm about to do is I'm about to take advantage of one of the identities that I showed you earlier in the chapter. I showed you the relationship between sine squared and cosine squared. And what I'd like to be able to do is essentially take this sine squared here and to ultimately make it into a cosine squared. So here's how I'm going to do that. I'm going to make this 1 minus 2 times, and then remember sine squared of theta is really just equal to 1 minus cosine squared of theta, right? And then we're going to do a little simplification. That'll give us 1 minus 2, I'm distributing the minus 2 right now, plus 2 cosine squared of theta. And then I can just bring that 2 cosine squared theta to the front. And then 1 minus 2 is negative 1. I can just put that in the back. Okay, now, again, I'm just going to pick an angle that we know and show you that this works. Always the cosine of 2 theta can be found by doing 2 cosine squared theta minus 1. Let's pick another angle that we know. Let's say 45 degrees. Well, according to this equation, then, the cosine of twice that, 90 degrees, should be equal to 2 times the cosine squared of 45 degrees minus 1. Now, we know that the cosine of 90 degrees is 0, and we know that the cosine of 45 degrees is the square root of 2 over 2. So we'll have 2 times that squared minus 1. And we're just going to show that both sides are actually equal to 0 here. On the right side, if we square the square root of 2 over 2, that's going to give us 2 over 4, or really just 1/2. Hopefully you can visualize that. And then I think you can agree with me that 2 times 1/2 is 1, and 1 minus 1 is 0. So we ended up showing that 0 is equal to 0, that the left side and the right side are equal for any, we picked an angle, we could have picked any angle we wanted to, and this equation would have held true. All right, there's one more version of it that I want to show you. It turns out that the cosine of 2 theta can also be found by finding the difference in the squares of the cosine of theta and sine theta. All right, now I'm going to build on the previous identity that we just learned in order to show you how to find this identity. Now this time I'm trying to make an equation that involves both sine squared and cosine squared. So I've got to be able to take this side of the equation and somehow introduce a sine squared since it's not there. Well, what I'm going to do is I'm going to use this 1 right here to introduce a sine squared. Now I'm going to leave the 2 cosine squared like it is, and then I'm going to put minus. And then I'm going to use one of those identities we talked about earlier. Remember that the sine squared of an angle plus the cosine squared of an angle is always equal to 1. So I can replace 1 with sine squared theta plus cosine squared theta. It gets pretty cool to do all these little substitutions and so forth and see that it works out. Once you get the hang of it, you really enjoy it. All right, now let's go ahead and distribute that subtraction sign. That'll give me 2 cosine squared theta minus sine squared theta minus cosine squared of theta. And then if I have 2 cosine squared theta minus 1 cosine squared theta, that's going to equal a 1 cosine squared theta. And then I've got minus the sine squared of theta. So always the cosine of twice an angle is equal to the cosine squared of the angle minus the sine squared of the angle. And I'll just show you one more time that this works out. Let's use something in radians this time. Let's suppose we let theta equal pi over 2. Well, twice that then would be pi, right? So we'd be saying that the cosine of pi equals the cosine squared of pi over 2 minus the sine squared of pi over 2. Alright, now what is the cosine of pi? Well, that's negative 1. The cosine of pi over 2 is 0, so we'll have 0 squared there. The sine of pi over 2 is positive 1, so we'll have negative 1 equals 0 squared minus 1 squared, and I think you can see how that would give you negative 1 is equal to negative 1. Alright, so again, identity is true for every value of the variable in the equation. I don't care what angle you pick. The cosine of twice an angle equals the cosine squared of the angle minus the sine squared of the angle. Alright, so this is how you know what identity is, and let me just kind of summarize those identities for cosine of 2 theta. Here are the double angle identities for cosine. By the way, you'll need to know these to make solving trigonometric equations easier. You'll learn later how that works. But the cosine of 2 theta is always equal to 1 minus 2 sine squared of theta. And each of those are always equal to 2 cosine squared theta minus 1. And those are all equal to cosine squared theta minus sine squared theta. Thanks for your attention. Hope this helps you well. Later.